Decided that what I'm going to do for like some of these, this might spill into next week a little bit depending on how deep we go. So I don't want to take too much time up today, but I do want to cover some things. So I want to explore the data a little bit, and then I want to also use these sessions to go back into some basic theory stuff so that when we do modeling stuff later, we know what we're doing. So we'll do a little bit of that. So a little mathy stuff intro and then go into the data exploration. So I want to take a step back real quick before we continue and talk a little bit about, again, some of the basis of the hypothesis test and the things that we do. So typically we will use R and we will fit some sort of a model like, like that, right? Something like that. Fitting some sort of regression model. And when we fit this, what have we learned so far? We've learned that these functions end up looking something like this, right? And these variables are things that come from your design. They could be anything, right? Like they could be numbers, they could be categories. We've talked a lot about categories recently. We started by talking about numbers. In the case of categories, this means we have a system with 3 categories because maybe this variable takes on a 1 or a 0 if category B maybe, and this takes on a 1 or a 0 if category C. And we learned that, in these sorts of models, if we wanted to get whatever the expected value is for YA, which would be the mean of A, right? That's just the B0. And then the mean of B is B0 plus B1. So this is the offset, the difference between those two means. Mean C, B0 plus B2. And we also learned that if there can be interaction terms, like maybe you have like a slope with time, so then you have some sort of B3, which is the interaction of like one particular group, some slope with time, and then maybe you have a B4, which is the interaction of some time with some group, and B5, which is some other time and some other group. So like, for example, maybe we have a general slope that's associated with A, so maybe in this case, YA is some sort of function that's B0 plus B3t. That's YA's slope over time. YB is B0 plus B1 plus B3 plus B4. T. So maybe that's different. Maybe group 2 looks like that. I don't know. And then, where's my mouse? There it is. And then group C, B0 plus B2 plus B3 plus B5. T, maybe group C has no relationship with time. That's fun. That's a very fun interaction. Look at that. So this is drug number 1, drug number 2. This is a complicated model, but you see how you can combine all those things. You could either have a simple situation with just means, or maybe interactions with time, or interactions with some other variable. These other things are representing some sort of offsets for the slope, and then these things are representing offsets for the like average value or the intercept or whatever. So we kind of learned all those things. And then we also learned that you can make any hypothesis test that you want, right? So the first hypothesis test might be, okay, let's just do the simple case of this. A first hypothesis test might just be, are these coefficient values equal to 0? That's a hypothesis test. What does that mean? Well, B0 is an intercept. We expect that to be not 0 because your typical amount of whatever is some non-zero number, but might not be the case. There might be systems in which you do expect the intercept to start at 0, right? So maybe there would be a situation. But when we're talking about group means, if this is the mean of a control and the mean of a drug, this is going to be some non-zero number. So it's unsurprising that this thing is not 0. So that's not really of interest. But this coefficient, we might be interested in knowing that this thing is not 0, because in this simple case, this represents the offset, i.e. the change, right? So that's interesting to us. So how do you construct that hypothesis test? We learned about Anova before, that's just the simple case of, well, what if we got rid of all of this and we just looked at the mean of all the data, right? That's the null hypothesis. We compare those two models and see how much this model does better at prediction. That's the basic test. But if I actually want to know if each of these, if I want to know if each of these things is individually different from 0, or alternatively, if I want to know if some combination of those things is different from 0, because of course, maybe the difference between two groups might be the difference between any of these two values or something like that. I can construct any of those hypotheses that I want, right? But the basic form of them is, suppose I want to know this hypothesis test, right? Where the null hypothesis is that this, whatever this value is, which is of course the delta in this case between maybe mean B and mean A. But it could also be a slope, like if you have a line and a slope. You're testing, so if it's a slope, if you actually have an equation of the form of like this, where it's like this, you might, the hypothesis test that this does not equal 0 or does equal 0 is testing whether or not you got a flat line or you have a real relationship. Right? So it's the same thing. It's 6 of one, half a dozen of another. You can think of them as slopes or as group differences, which is why it's one basic united analysis. So the null hypothesis is that this particular value that you're testing is equal to 0. That's the null hypothesis. And the alternate hypothesis is that it does not. It equals something else. Okay? Okay, cool. So how do you do that? Well, we've sort of practiced this a little bit in terms of how to code it, but just to review, the way you do that is you take that value and you divide it by some estimate of its standard error, of its uncertainty. Oh my God, I'm pressing the button on this little thing. Okay, when you do this, whatever this uncertainty estimate is, which comes from the variance in the model, this is something which we call t. Okay. So t is a t-statistic, and the classical t-statistic you think of very often is, you know, the mean of A minus the mean of B divided by some pooled estimate of the standard error of A and B. Huh. Oh my God. Right? Something like that. That's the classical hypothesis. But if B is a slope for like a y equals b0 plus b1t, still, in linear regression, this comes with some estimate of uncertainty, right? So if you want to test any hypothesis, no matter what it is, that some b1 equals 0, well, your numerator is just b1 minus the other side, which is 0, so that's just b1, divided by some estimate of the standard error. Okay, that standard error comes from the model, and so in the model, we have a b0 and a b1, and we call this the var-core, or the variance-covariance matrix. The way you get access to this in R is using this function, the vcov function. Okay, and down the diagonal are the squared uncertainties for each of these statistics. Okay, they come from the fancy linear regression model. I'm not going to go into that too much right now. On the off diagonal, typically we expect that these things are uncorrelated, but there may be correlations between these two statistics depending on how much correlation is in your data. And so there are off covariances. So this is the SE in B0 times the SE in B1 on both of the off diagonals. We'll learn about covariances some other time, but primarily you need the diagonal terms. Okay? Okay, so then you have the diagonal term. So you just take that value, you throw it in here, and this is called t. Okay? So this is in general the case. So you can tell that, so this is where one of the assumptions, by the way, of linear regression comes into play. One of the assumptions of linear regression, Anova, all the things, is that you have something called homoscedasticity. That's really ugly looking on here. But what this means is that if you have grouped data or data with different levels or things like that, no matter which level you go on, you can expect the variances in those groups to be similarly spread. Now, this isn't always the case in real data, right? But what this assumption means, this ends up having a very specific effect in this matrix of uncertainties. What that means, that assumption does the following. Suppose I have B1, B2, and B3, and these all represent the offsets from various groups. If, this is the case, if n of group A equals n of group B equals n of group C, which is like what we call, or in this case, there are actually 4 groups, right? Because there's also a B0. If there are 4 groups, which means you have 3 of these betas that you need, which are differences between one of the groups and the other ones. If they're all equal in size, this is called balanced design, right? That's very nice design. What that means because of homoscedasticity is that linear regression is going to predict standard error, well, I can't pick the same way I want to draw E. These numbers will all be equal to each other. Okay. That's if they're balanced design, because it scales to some degree with n based upon the original formulae for how these are determined. Now, this might actually be a bad supposition to make. So you'll notice this. We noticed this before. I think we did one data set. I can't remember which data set it was. Maybe it was one of Maddie's where there was the same number of n in each thing. And if you remember when we looked at all the pairwise tests of the things, the standard error for each of those statistics was identical. And that's because of this assumption. Because this assumption picks one basic value for sigma squared, which is considered the error in the model. This is the model uncertainty. And then the rest of this is all solved by using this fancy thing, which is x transpose x inverse times sigma squared. This is how this matrix is determined. Okay, you can look this stuff up some other time if you really want the nuances of that. But because of this assumption, this might mess up some of your tests if your data really strongly violate this assumption, right? Because linear regression will just produce this based on this one scalar value and how this scalar value is weighted for each of these coefficients. And if you have balanced design, that's going to be identical for all of them. So that's not necessarily the best idea. What we're going to use today a little bit is there have been various proposed corrections by numerous people to how to fix this problem for when your data violate this assumption. And so there is something called the Huber-White estimator, which is a compromise between 2 different econometric statisticians, one named Huber and one named White. There are various different ways that you can take these and multiply them by some kind of a scaling factor that's like maybe group specific, something like that, to sort of deal with this issue. If you think about it in the simple problem of just calculating means, how do we do this? Well, when we calculate means, like just a single mean, if we just have a mean of A and a mean of B, there's a statistic that we can use which is a weighted, or not a weighted, but like a square root of the sum of the 2 individual variances, right? So we call this the pooled standard error estimate, right? So you often have this sort of sitting in this very simple situation where you have mu B minus mu A divided by the square root of sigma squared A plus sigma squared B. You have something like this that you can use. And individually, these things, we also have these like terms. Oh, and there's like an n minus 1 somewhere. I can't remember where. The individuals, it's probably n of A. There we go. N of B, where this is the actual sample standard deviation, right? So you can use that kind of a statistic, where the sample standard deviation, the standard error of the mean for like a single sample, we typically call, what is that? The variance, the square root of the variance in whatever that group is divided by the number of things that are in that group. Sometimes minus 1, sometimes not, depending on the estimator you want to use. That's cool. So standard deviation by the square root of n. That's called the standard error of the mean for a single sample. So in the linear regression level, you can make corrections like this, okay? Those use different matrices and different types of corrections that I'm not going to belabor, but if you look in the documentation for one of the packages that we're going to use, you can link to papers that discuss all the possible different corrections. And one of those papers actually did models that decided, oh, this one is the best after lots of simulations. So you can just decide which one you want to use, but we're just going to use the default today. So then basically what you get to do is then pick that, instead of using, whoops. So you have this thing, right? Here, I'll just do the simple case with 3 things here. instead of using this thing, using one particular package called the sandwich package. This stands for heteroskedasticity consistent estimator, I think is what it stands for. And of course, you can pass more parameters to this that pick your favorite one from the literature that you actually want to use, because there are, I think, 5 or 6 different corrections that are built in. You have the same thing. Oops. But now these estimators are replaced with estimators that come from that particular correction. Okay. And the fun fact is that the fun part of this is you don't have to really do much of this by hand. For a lot of the functions, like the Anova functions and the multiple hypothesis functions, all you have to do is tell those functions to use this instead of this in its underlying functions. There's a simple parameter to do that. Okay, so that is nice for when some of those things have pretty extreme violations, which I have a feeling in these data you're going to have some pretty extreme violations, just because we know that there are lots of differences, and especially in some of like the no-shot groups, if you have lots of zeros or things like that, those variances are going to be really, really different. So you probably want to use the best estimator you can to do that. So we'll show you how to do that. So that's what the sandwich package is going to use. And this gets to get past, you can pass this particular variance function to both the Anova function by just specifying that you want to use that thing instead of what the built-in one would normally be with the assumption of homoscedasticity, as well as when you go ahead and do your various like multiple comparisons functions, you can pass this function into those and it'll come up with more robust estimators of all those standard errors, which is nice. Cool. Okay, great. That's kind of all I need to go into that mathy-wise for now. We may go into more detail on how some of those things are calculated. Oh, but finally, once you've decided that you have this t-statistic, so you have whatever you've decided, here's your estimator you want to care about. In this case, maybe B1 equals the change in means between group A and B, whatever it is, a slope, something like that. Now you have some estimate of what the standard error in that is, whether it's the one that comes for free or the replacement one that you've decided is a better estimator. This is called T. And for those who don't know, T is the student's T distribution was defined in the early 20th century by an anonymous paper by someone who used the pen name student. That's why it's called the student's T distribution. And describes a distribution which looks like a normal distribution, but it's a little more taller and skinnier than normal distribution, usually. It has different shapes. And if you think about this, this is the null hypothesis. So the null hypothesis under a T distribution is centered on 0. Remember, that's your null hypothesis, is that B1 equals 0. So under the null hypothesis, you expect that it have the value of 0. And then it has other values, it takes on other values. By taking your estimate and dividing it by the standard error, you've completely removed the units. It's a unitless quantity if it was originally in seconds or time or whatever. So this puts it on a standard scale, which is what T is. So any number in the world, the theory is that you've now put it on a standardized scale, right? So this is now a score, basically, right? And so whatever your T statistic is, +1, -1, +2, -2, et cetera, you take a look at your actual value for this. So let's pretend our actual value for this was 15. And you see how probable on the standard student's T distribution would a value of 15 even be, right? So let's pretend that's out here somewhere. So then what you say is, what's the area under the curve? What's the probability of seeing values this or bigger, right? And that's what a p-value is for the T distribution. That's what the t-statistic is. And in practice, we calculate something called a two-tailed p-value, which means we don't have any a priori hypothesis as to whether it's plus or minus 15, and it could be either direction, because you could just have specified in your model. You could have specified that the wild type is the second level and the other one is the first. It could just as easily be -15, right? It could be either direction. So what you do is you find the -15 on the other side. It's completely symmetrical, so this is the same probability on both sides, and you add those two things together, and that's called the two-tailed p-value, okay? And if you had a value that was over here, let's pretend it's 0.5 or something like that, this is obviously very probable, right? According to this distribution that I've drawn. And so your significance criterion is based upon whatever your probability is according to this null distribution. If this is very probable, that means it's still within the bounds of what could be close enough to 0, at least in your estimation, right? And that's based upon our very arbitrary alpha of 0.05. We think that things that are bigger than 0.05 are reasonably close to being 0, basically, or indistinguishable from 0, and things that are less than that are really far away. So one thing that controls the width of this thing, depending on your data, you might have a t null hypothesis that looks like this, in which case your p-value is really, really tiny. Or you might have a t statistic distribution null hypothesis that looks like this, in which case it's more probable. So does anyone know from a basic statistics class what controls the width of the t's null distribution? No one knows? That's right. It's something called the degrees of freedom. This is the last thing I'll explain before we work with the data because it's important. OK, so there's one parameter. So in a normal distribution, you have a mean and a standard deviation. All these distributions have things that are called parameters, right? And the parameter that controls this, because remember, we've gotten rid of this t-value has gotten all the units gone. It's just a single score, OK? So the thing that controls the width of this distribution is a particular parameter, which historically is called the degrees of freedom. It's sort of a good term, but it can be confusing. So I'm going to explain it in a machine learning way. You have data. Here's your big matrix of data. And every row in your matrix is an observation. So you have n observations. That's your data points, your actual data points that you have. And then you fit a model. And you have these predictors that you're trying to estimate. How many different things are you trying to estimate? So you have k predictors. In this thing that I just wrote, I have 3. And let's pretend we have 100 observations in our data set. Okay? We define the parameter degrees of freedom as being equal to n minus k. Okay? So in a machine, this is a machine learning sense. You'll often see it defined in like classical group statistics as the number of observations minus the number of groups minus 1, or like there are a bunch of different things, or minus the number of groups. Like there are a bunch of different ways to talk about it. This is a nice general way to talk about it because this becomes true even if you're just fitting a line equation like with a slope and time, just like a standard curve. You're trying to fit 2 things and you have n data points, right? So the degrees of freedom is an estimate of how much data you have as a ratio sort of how many things you're trying to estimate, right? So what do we know? Josh, can you tell the class what overfitting means?
When you rely too much on your training data that your model does bad on testing data?
That's a very general way of understanding it. In terms of n and k, what does overfitting mean?
You have too many predictors?
Yes. So think about it this way. When k is very large, or approaching n, the degrees of freedom is very small. If df is very small, the t distribution is very wide. Okay? So that's what that means. So that means you get penalized for trying to predict things that are approaching the number of data points you actually have. Okay? If n is very, very, very much greater than k, you're only trying to predict a couple things and you got thousands of data points, then you get a boost because then anything you estimate is going to be really precise, so your t distribution is really skinny. Okay? And most data sets are somewhere in between. At some point, k can never exceed n. I mean, literally it can, but then if you try to solve the systems of equations, the inverses don't work and nothing works, and so then you crash. So you can't have k exceeding n, but k can approach n, and when k gets close to n, then you penalize your probability distribution for your null hypothesis, which seems sensible. And in a very just English readable way, you don't have enough data to support the number of things you're trying to estimate, right? So in general, it's a good idea to have a lot more data than you have things that you're trying to estimate. And so that's what that value is. And mathematically, this controls what the width of this thing is. Okay? So if you have lots of data and you're trying to predict relatively few things, the more data you have, the more precision you have on that. What does that mean? If you think about it in terms of the actual p-value, if you have a t null distribution that looks like this, and you have a t null distribution that looks like this, if k is the same in both cases, the only difference is that this one has n2 is greater than n1. That's the only difference. If k is the same, then the reason why this distribution is skinnier is because there's more n. You have more data. So if that's true, and you're trying to test what the probability of observing something, on the null distribution, let's say a value of 3. Oh, you're good. You can come through if you want. If you're trying to predict the value of 3, or let's say 2 or something, in the case where you have more n, you can see that probability is really tiny. But in the case of where you have less n, that probability is larger. Okay? So n increases your chances of... Now, at some point, you're impinging on when something is so close to the 0 value that doesn't make a difference. But for most things, it will make a difference. So depending on where your thing is, if you see, for example, suppose you have this. There's a difference between a t value that's like really close to the center, like this one, and a t value that's like here. If you have a t value that's here, that almost suggests that there's a trend in the data that even if p is less than 0.05, if you increased data and the t value stayed in the same place, you would achieve p less than 0.05. If you have a t value that's really close to the midline, probably it doesn't matter. So these are things that you should assess. So what I mean to say is that sometimes people will look at the p-value just as the straight-up number that it is and not look at the other statistics that go along with it and then decide, there's no difference. But actually, there might be, you might not have enough data to appreciate it, so you can make decisions about whether or not it is worth your time to collect more data or not, is sort of the point that I want to drive home. Okay, great. Now let's play with the data. So the way that just so that I understand, Megan can tell me if I'm wrong about any of this. But the way that this experiment is done is after the conditioning round, which is what we did last week, where they get a tone and that's paired with a foot shock. Now you do the testing round on the next day. So if they have been conditioned, so they did get a shock, the expectation is that now if you play the tone, they'll freeze because they think a shock is imminent. Right? So that's classical Pavlovian conditioning. You ring the bell and the dog comes running because it thinks food is going to happen. Eventually you expect, I think I zoomed out by accident. You expect that maybe over time, if you keep repeating the tone 1, tone 2, tone 3, tone 4, if you keep repeating the tone and there's never a shock, eventually you expect this learning to extinguish. So the dog originally associates the bell with getting food. Now you ring the bell, the dog expects food, you don't give the dog any food. The dog's like, oh, okay. You ring the bell again, the dog comes running again, there's still no food, and it's like, what the hell are you doing? Why are you messing with my mind? Then you ring the bell a third time, and what might happen is the dog might stop coming. The dog realizes at this point that there's no food, it's not a real association anymore. So similarly, you might expect that the freezing time with repeated tones with no shock goes down, and that's called extinction. Okay, so that's when a memory is going away, or an association rather, a learned association is going away because there's no more reinforcement. And you can imagine that different drugs, different conditions, different mutations, all those things can affect how quickly the memory gets extinguished, or retained, or whatever, or maybe even conditioned in the first place. In this case, they are specifically looking at interactions with sex as well of the animal. But regardless, it's the same kind of paradigm. That's the hypothesis, is that you have some sort of a negative slope with repeated plays of the tone. This is day 2, there's no more shocking. So there's some animals that there's some animals that are in the no shock condition. That's a control. These guys should have never made an association. If they freeze, it's completely by chance. So if they freeze at all, then their freezing rates should all be down here somewhere, just in general, even if they do it a little bit. And it shouldn't really change from one to the next. But the animals that have been in the shock condition, those guys allegedly have been conditioned, which means when you put them into the testing arena and you play a shock, they should freeze more. And that eventually this may decay over time as they extinguish that. So there should be two patterns. There should be a no shock pattern, which we expect to be flat and low, or maybe non-existent. And we expect the shock pattern, which looks like this. And if there's some interaction with sex, there may or may not be, then that might change the slope of this line. Now, we don't expect the sex to completely change the relationship. We wouldn't expect the sex to do this. That seems unreasonable. However, another interacting variable like that might change how quickly it extinguishes. So rather than be a very steep line, maybe it's a steeper line, or maybe it's a slightly flatter line, something like that. You still expect, regardless of this particular case, I think Megan would still expect that it extinguishes eventually. However, it's possible that other variables might slow that rate or speed it up. Okay, that's the expectation. But this kind of interaction here, where the lines actually cross, that fundamentally change the nature of the relationship, I don't think we would expect that for these kind of data, but you could expect that there may be other situations and other kinds of data where a drug or something completely fundamentally changes the direction and magnitude of the thing. Those are all possible. But for these kind of data, it's probably not expected. So the way that I did this is the data were split up in a few different ways. So basically what happens is the animals are tested for about a minute, and they get 10 seconds of the tone being played, and then an additional 2 seconds after the tone is played, when normally the animal might expect that a shock would occur. Okay?
Final 2 seconds of the tone is what the shock will be.
Wait, how long is the tone again?
10.
Oh, so it's 0 to 8 and then 9, 10.
0 to 10, 9, 10. So it overlaps.
Yeah. Wait, what do you mean it overlaps?
So
0 to 8 is the tone.
0 to 10.
0
0 to 8 is only tone. 0 to 10 is tone, and then the last 2 seconds.
Sure. So 0 to 8 is only the tone.
Yes.
And then seconds 9 and 10, or excuse me,
Tone plus expected shock.
it's technically 0 to 7, then 8 and 9. But regardless, the way you have to frame, yeah, but you see what I'm saying. From the first 8 seconds, a tone is played. The final 2 seconds, no tone is played.
Tone continues.
The tone continues during the final 2
So
seconds.
when they were getting shocked, the tone is still playing.
Oh, okay. So the tone is playing the whole time. It's just whether or not you're analyzing the first however many seconds versus the last couple seconds.
Yeah, so 8 seconds, maybe they're actually running around because they're like trying to find a place to hide or something, and then those last
I
2
see.
seconds they freeze because they give up or
Got it.
something.
So then these values for the value of t are kind of incorrect. This should be 0 to 7, then 8 and 9. I'll fix this later. I don't think we'll do this particular thing because this I have to fix this column because it's not correct. That's fine. But I'm going to consider this one. This is the total count of the number of freezing bouts, or the total time in seconds spent freezing during that entire 10 seconds. Right? So I'm calling it tone 1, tone 2, tone 3, tone 4, but this is not considering any distinction between the first however many and the last 2 seconds. So this is the data set that I'm going to work with today for exploration, just because it's the simplest. But then additionally, I've split it up into 2 other sheets. The tone only sheet, this is just that 8 seconds of tone. Okay? And then the expected shock is just that final 2 seconds, and you can see there's a phase: shock 1, shock 2, shock 3, shock 4, shock 5. Okay. Cool. Great. So I'm just gonna look at the tone plus expected time, because that's it's the sum of that whole for each of those things. Is there a rest period in between, or it's like okay? Do you actually determine how much freezing happens during the rest period at all?
I didn't export that.
Okay. All right. Well, good to know. So how much rest period is in between?
30 seconds.
30 seconds of rest. Got it. Okay.
Yeah, so same thing that they had on day 1, except I just extended the number of tones.
I see.
that were distinguished.
Got it. Okay, great. So, so I'll fix this time one, which is an actual time trace I'd have to fix what the t-values are because I messed it up.
Yeah, I can write it out.
Yeah, it's fine. Or yeah, you can do that if you want. Or you can use whatever we do in here as a template and then just analyze it yourself. This, of course, if we did a model with time, we might consider it as an actual continuous number and like look over time as a slope more than like groups. You can kind of decide how you want to do that. But I'm going to focus on this one. We also have a habituation period, which is 3 minutes at the start of the experiment. So there can be differences there, but this is a little bit separate from the whole paradigm. Okay. So, but we're mostly going to pull from this sheet today for exploration, but you could analyze the other sheets. Cool. So I'm going to go into R. So go ahead and load up, if you haven't, load up, I would run through line 32. And I'm going to introduce you to this type of structure, and I'll make sure your directories and all that's correct. If you get some errors, let me know, but this is all pre-written, so hopefully it's fine. Run through line 32, and then I'll explain what that little loop thing is doing. So when you have done all of that, raise your hand, and then we'll continue.
Invalid multi-byte string.
Excuse me? Yeah, there's no, don't do this. Did you run this?
Yeah.
That isn't in the original code.
Oh, I added it.
Yeah, don't do that. Yeah, we're not doing that. Because there's no CSV file. Yeah, there's no CSV. We're reading direct. Yeah, we're reading direct from Excel. Yeah, don't do that. Yeah, just run as is, and that might be probably why it did that. There you go. Cool. So did everybody else? Is everybody else's thing? Josh, you're looking confused.
So cannot find the function read_Excel.
Did you install the read Excel package? Yeah, maybe I didn't put a comment next to that one, but the expectation was that maybe you don't have that. Yeah, whenever you run, okay, so if you were to run this, I mean, you just run the whole thing and then it gives you an error. But if you run the library read Excel thing and it gives you some error, it's because you don't have that installed. So then you might need to install that. So after you install that, then you can, because reading Excel files is not built into R at all. You have to install an extra package that some person wrote to do that. So what does this do? I'm just going to explain briefly, so don't do any necessarily typing, but you can just look on the screen. Maddie, did you run all that? It's fine? Okay, cool. So what capital D is something called a list. So a list is a new type of data structure that I haven't really gone over yet. So you may recall, a data frame is something that looks like, I don't know, 1, 2, 3, A, B, C. Okay, so this is a data frame, right? You got 2 columns, and they have different data in them. What a list is a list enables you to have multiple data frames. You can have any it's kind of like in MATLAB, if you're used to MATLAB, there's something called a cell array. And in a cell array, each cell can have anything you want in it. So it could be a number, it could be a whole data frame, it could be a file, it could be a million different things. And so what capital D is each of those sheets imported in as its own data frame. So for example, if I look at str of capital D real quick, you'll notice that there's a bunch of things in it. So there's a particular sheet which is called HAB. That's a data frame that has all the HAB stuff in it. Then there's another one called tone that has all that stuff in it. Then there's another one called expected shock that has all that stuff in it. There's an experiment, all that stuff in it. So if I look at this, if I looked at view D, HAB, and you can access this if there's this issue on my computer right now where my number 4 key doesn't work, so I can't do a $ at all. So it's time for a new computer. But you can access any element of a list using this double bracket notation as well. So if I look at dhab, you can see that's all of the data from that particular sheet that's labeled HAB. Okay. So basically what this loop has done is for each thing, so I've said for each sheet, tone, expected shock, tone plus expected shock, and time, I said I want you to read that Excel sheet and put it in as a new element of D. So basically D is like a book of 4 different sheets in it. Okay? So there's individual data. So it's a nice way to store all of those in one big mega thing. So then if you wanted to, you could access each one individually. But they're not. It's not all one big table. It's like a booklet of like multiple tables, if you want to think of it that way. There's a big if clause in here. You'll notice it's the levels of that phase column are different because sometimes it's tone 1, tone 2, tone 3, tone 4, tone 5. Sometimes it's shock 1, shock 2, shock 3, shock 4, shock 5, something, something, etc. So depending on which sheet I'm reading, I set those levels appropriately. So that's what that part of the loop is. So if you look here, you'll see that in the dhab sheet, there is no, it's just a character. There's no factor there. There's no levels. If you look at the D-tone sheet and you look at phase, it's a factor with 5 levels, tone 1, tone 2, tone 3, tone 4, tone 5, et cetera, et cetera. If you look at expected shock, it's a factor with 5 levels, shock 1, shock 2, shock 3, shock 4, shock 5. Tone plus exp is tone 1, tone 2, tone 3, et cetera, et cetera. And then time is tone 1, shock 1, tone 2, shock 2, tone 3, shock 3. If you look in that code, this line here, line 28, at least in mine, unless you've added some stuff, if you look at what this has done, this is just very quick and easy way to get a thing that says tone 1, shock 1, tone 2, shock 2, tone 3, shock 3, tone 4, tone 4, tone 5. Doing this without actually typing all that out, because I didn't want to type all that out. One thing I want to note to you, if you quickly need, you can use this paste 0 function. See how it says the word tone, and then it has the sequence 1 to 5? This does something nice, which is it just makes this vector, where it pastes the one thing to the other thing. So it basically takes the word tone, and then it takes the sequence 1 through 5, and then it takes the sequence 1 through 5. Oh, then my 5 key doesn't work either right now. Oh, I hate it. What's up? What's up? No, I did that on my computer before I came in here. So it takes this, and it takes this, and it just combines them and makes this. Or whatever, or this one. So the paste function is super nice. The paste function, by the way, in general is a nice function for hello, welcome to the other half of the sentence, and makes it one thing. Okay, so the paste function is a nice way to do that. The paste 0 function does it with no space in between. The paste function does it with a space in between, or any character you want. Okay, so these functions are kind of nice for just like smashing letters together. Cool. So this is explained in the comments here. D is a list of 5 data frames with similar structure. So there's a hab, a tone, an expected shock, this tone plus expected shock. Note, when I use the $sign notation, I have to wrap anything. See how there's a plus sign? Plus is like a normal arithmetic thing. So if I were to write in R, if I were to write this plus exp, it would expect x to be a variable that I'm trying to add it to. So that's not good, right? Because the plus sign is, in general, you shouldn't use plus, minus, equals. You shouldn't use those sorts of symbols in the name of something, because then that can mess things up. But it's not that big of a deal. You can wrap it in the accent grave, and then it deals with it. Okay? Okay, so I'm going to specify little d, which is the normal d that I use in all of my code for like the data set that I'm working with. That's my little notation. I'm going to set it to be this particular one for the rest of the code. But if you were to go back through and pick a different one, you could just reset it. Okay, so that's what line 49 is. And so then if we look at d, little d, that's just all the data that should be, this is the sum of that whole 10 seconds again. So in this case, for this particular animal who is female in the shock condition, received, or excuse me, it showed 2 counts of freezing bouts and a total of 4 seconds spent freezing during that entire 10 seconds, and that's what it is. Okay, so does everybody have, does little d work for everybody, and everybody has that? And if you do a head on it from the console, again, you can view, the view function opens it up in a new tab, and the head function just shows you quickly in the console the first handful of lines. So it's a nice way to just quickly see what's going on and make sure all the columns are the way you want. You'll notice that I made this other column called animal 2, which is basically the first 3 columns smashed together. I did that because I noticed there were a couple cases in which there was like a cohort 3 without the word novel and the same animal number that seemed to be maybe like they weren't unique or they were unique or they were independent. I wasn't exactly sure, but I wanted to have a column where each animal was completely unique. And so I did that. Megan can decide later on when she looks at the data all those things, what they mean, and decide to there what is unique and what is not. So I'm going to go over a couple things because we haven't really done too much of this in the past when we were just learning how to use the base functions in like analysis. But I'd like to do a little bit of analysis of just how much these data deviate from some of the assumptions of normality and homoscedasticity, which we've talked about before. So the first way that I do that is by plotting a histogram. So if you haven't done histograms in R yet, it's just using this hist function. And in the hist function, I'm saving this to a particular variable. So if you run line 55 real quick, and run line 55, and then display counts hist from the command line, you'll see what it looks like. So these are the bouts of freezing counts. So what does this mean? This is from the whole data set. What it does is it says, okay, anybody between 0 and 1 count how many of those there are. There are 99 of those. And between 1 and 2, 19. And between 2 and 3, there were 9. And between 3 and 4, there were 7. And between 4 and 5, there were 1. And I guess there were no more than 5, really. Okay. And then those counts are important. The density is maybe less useful. That's the like peak height. I actually prefer for histograms something called frequency, which is basically the number of counts divided by the total. The density is the number of counts divided by the total divided by the break size, because the break size might be different depending on your data. In this case, it's pretty easy. But I'm going to go ahead and run line 56, which actually counts what the sum divided by the sum is. So it's a little bit easier to interpret. In this case, it's the same as the density because the break size is just exactly 1. And so that means 73% have between 0 and 1 freezing bouts. 14% have between 1 and 2 freezing bouts. 7% have between 2 and 3. And progressively fewer percentages have less than that. Okay? So you can plot this. And so that's this plot that I do right here. That's lines 57 through 62. That makes a plot that says my figure margins weren't large enough. I'll run it again. Okay, like this. So this is the histogram of the data. And depending on what the data look like, the histogram might look something different, but you should receive something that looks like this. There's obviously still a preponderance of zeros, or things that are low between 0 and 1. And that's probably because we have all those no-shock animals, which probably aren't freezing very much. And then what I'm showing you in these next things are what the histogram would look like if the data were really normally distributed with the mean and standard deviation that they have. So the bin width is just 1. But I'm calculating it anyway. That's the difference between 2 breaks, right? So what is the width of each bin? But then the expected normal comes from this d-norm function. What is the d-norm function? That is the probability density function for the normal distribution. So from a normal distribution with a mean equal to the mean of the counts that you have and the standard deviation equal to the counts that you have, you can figure out what this curve should look like. Okay? That's from just the standard calculations for the probability density function for the normal distribution. And in R, probability density functions always start with the letter D, and then there's like a code for what kind of distribution you want to pull. So there's a DPOIS for the Poisson distribution. There's a DBINOM for the binomial distribution. So each of these has a very standard way of pulling the probability density function for each of those things. And then you can kind of plot that alongside it, and that looks like this. So obviously the data are skewed from normality. That's not unexpected because first of all, in our real world data, we can't have negative values. Remember, the normal distribution looks like this size because I'm only looking at this range of it, but actually technically the normal distribution is perfectly happy saying there's another side that's symmetric that goes this way. But we know that the data are bounded at 0. We know that we can't have more than 0. So there's going to be some significant deviation from normality. There's no good way to quantify this, really. Everybody has their preferred test. Most tests of deviations from non-normality, even if your data are very normal looking, will still say that it's significantly deviated from normality because they're very, very, very sensitive. I tend to look at I'll explain QQ plots maybe next time, but I tend to look at some sort of simple measurement like an R² value. Like if this is my expected histogram and this is my observed histogram, how similar are they? Just a similarity metric between two histograms. This says maybe 52% of this data could be described by normal distributions. It's pretty non-normal. What does non-normality mean for regression? What non-normality means for Anova and regression typically means a hit to your sensitivity. That means pound for pound, you need more n per group to observe similar magnitudes of difference. That's usually what that means. So that's not necessarily a bad thing unless your deviations from normality are very, very large. Well, it depends on what you're trying to do. Let me say it this way. If you are just trying to say within the context of my experiment, do I detect something or not? We say very often that Anova and t-tests and all those things are very robust against violations of this assumption. The reason being is because you're mostly limited by your n. If you have high enough n, you can kind of overcome that, because the deviation from normality simply means you're going to have this hit to your sensitivity. You can improve that by doing more n. So for the most part, it's not that big of a deal. The problem can enter if you don't really have the ability to do more n, if that's challenging, right? But the second reason why the deviation from non-normality might be important is if what you're trying to do is not just test a hypothesis from the data that you have, but actually do a prediction about future data. If you're trying to do a prediction about future data, you really need to avoid the possibility that the model returns to you a number that's impossible, right? So if you're trying to predict the future, you can't have it say that the predicted value is -10 freezing bouts. That's impossible. So prediction is a different beast than hypothesis testing, but they're both important. So you can decide whether or not this is tolerable for you. And if you see something that trends a certain way, you can always add n to the story, usually is the way that you get around that. Great. So I'm going to do the same thing, lines 70 through whatever. Do the same thing, but for the time in seconds. Okay. And this deviates a little bit less from normality. The R² between these two histograms is a little bit higher. It's 0.63. That's to be expected because seconds, there's more of a range of numbers that are possible because it's a more continuous-like metric. So this is showing you the, this says bouts of freezing, but that's a lie. That's a typo. That should actually say time spent freezing in seconds. So you can fix the plotter xlab. That's the variable that is the label on the x-axis. So it should say time spent freezing in seconds. And it obviously misestimates the peak by a long shot, but the rest of the curve is mostly like reasonable. Okay. Again, we have deviations from normality. That's going to be a hit to sensitivity potentially. And we're always going to have a lot of zeros when we have this no shock condition where we expect there to be mostly zero. Now, sometimes that can run into some issues. If it were true that the no shock condition never froze even once, you would need to use a different type of hypothesis test or model to analyze these data because the complete lack of variation in that category would mess all the calculations up. Like you would end up with some infinities, some nada numbers, some other things, because it simply will not have an estimate for standard errors for those sorts of categories if there's like truly all zero values. So it will really mess that up. There are other potential models that you can use. You can always use non-parametric statistics or like other tests to test those things if you want. But assuming that you at least have some variation in there, we can actually see if that's the case real quick. If you look at D and look at where the D, oh God, I need to copy and paste a $sign, oh no. Where D, it's called condition equals no shock. And let me look at the time freezing, is that what I called it? Time freezing, yeah. We can actually look and see what the values look like. I'm just going to display it. This is what it looks like. If you look in the no shock condition, you can see there are some instances where there is non-zero values, but it's a lot of zeros for sure. So hopefully everybody should see that, and you can compare that to the shock condition. So the shock condition, you can see a lot of variation going on. And the no shock condition, there are a couple. It'll probably still return an answer, but it might be a little messed up. Is everyone able to like subset these and look at these? Yeah, cool. So what does this tell me? This tells me a couple things. One, it tells me that what I should consider doing is if I have issues running a hypothesis as compared to the no shock, is I could at least, at the very least, look at the time dependence between the males and the females in just the shock data. Right? What am I doing? Oh. Because if I have issues estimating this, like because of all the zeros, I can at least look at the differences in slopes in the shock condition. Okay? So potentially what we want to do is do 2 rounds of testing that are 2 different sort of models. One looking at no shock versus shock, right? And then the other one looking at just within the shock, what's the relationship over time. That might be something worth considering. Cool. Okay. And then finally, we're going to look at homogeneity of variance. So if you look at line 88, I'm going to run something called the Levene test. So the first thing in order to do the Levene test that I have to make a fake variable I'm not really going to use later, which is just all the possible intersects of like all these 3. There's a phase, there's a condition, and there's a sex, right? So you get tone 1, tone 2, tone 3, tone 4, tone 5. You got male, female, you got all of that. So I'm making this group because Levene test, for whatever reason, only wants one X and one Y. You can't make a complicated statement inside of it, unfortunately. And so I'm going to run one for the counts and one for the time. Okay, and if I just quickly Google the Levene test and look it up on the most reliable source, Wikipedia. Levene test wiki. Yeah. There's a parameter, which is defined as this big ugly thing. Okay, where each of these are the individual data points from their respective groups. That's on the bottom. And then on the top, you have each of the respective groups compared to the grand mean of all the groups. There's this big ugly statistic. And this statistic is estimating how different the variances are between the groups. Okay? And so, oh, and I should say that this statistic, which is W, so this is each of the values minus its own mean. That forms these Z values. This big ugly statistic has a null distribution according to something called an F distribution, which is the same thing Anova uses. So it has an F null distribution. It says, is this thing bigger than expected by chance if the groups were expected to all be equal to one another, which is the null hypothesis, is that they're all equal to one another. Okay, so what we see when we do this is that we have significant departure amongst the groups between that, which is maybe not surprising, and that's true for both of these. So what that means for us is that we need to use the corrected standard error terms, because we cannot use the assumption of homogeneity of variance. Because if we do, especially with all those zeros in there, those standard error terms are all going to be messed up. like it's going to assume that each one of those groups, regardless of whether it's the no shock, female, whatever, all exactly have the same standard errors, which is unreasonable, right? Because of the way the data are framed. And so since we have significant departure from that assumption, we should use the corrected standard errors based upon that. So to do that, I'm going to use this vcov HC function. And what you see, what I've done here is I've created this variable called varfun. That's not just because variances are fun, but it's just my variance function, okay? My variance function could be the just normal vcov function, or it could be this vcov HC function. And what's nice about R, unlike MATLAB and some other things, is that you can actually save a function name as a variable and then just use it, which is nice for the subsequent things we're going to use later. So just very briefly, I'm going to show you what this looks like in the notes here, and you can read about it. So this is called the heteroskedasticity consistent covariance matrix estimation. Okay. And there basically are a bunch of different options. The default is this HC3 option. They're all different corrections for those standard errors. And they're corrections that come from different people's papers over the years, basically. So you can actually look at all of these sources that are in here. The main source that I use for this is this Long and Irvin 2000 paper, which is using heteroskedasticity consistent standard errors in linear regression model. Basically, this paper assembles a bunch of different ones that have been used over the decades, and it does some simulations and decides that this particular HC3 one is the best. And so that's the default in this, and then there's some other ones. In practice, when I looked at all of them individually, they deviate by like a couple decimal places. So it's kind of like whoever wrote their paper, probably they use their favorite. You know what I mean? They all deviate a little bit, and they're all very close. If you do the mean by mean, they're very close to what the expected estimation would be by doing standard deviation divided by square root of n, like something like that. They're all similar to that. So they seem reasonable enough, so I just leave the default for now. I don't really have a strong opinion whether I like McKinnon's one better than White's original in 1980 versus Zeileis in 2004. I don't know. You know what I mean? So I'm just going to use the default. So I'm going to specify that here, and then we're going to go ahead and pass that into our models and our things later. Okay? So let's go ahead and test some things. I'm curious how well this tolerates all the zeros. So what we're going to do is we're going to fit model 1, and that's going to be everything. So that's the interaction of the phase, so which tone you're in, the shock condition, and the sex. So all of those things. So I'm going to say LM is, let's do the time freezing, because there's a little bit more variation in those numbers. So I think it'll just like work. Is that called time freezing? I can never remember. Time freezing, yeah. Capital T, capital F. So time freezing as a function of, let's do condition, so no shock, shock, times sex, male, female, times phase, tone 1, tone 2, tone 3, tone 4, tone 5. Okay? By the way, technically we should be using a completely different paradigm for this because these animals are repeated measures. I'm not going to discuss that today. We're treating these as every particular data point is its own animal for right now, which is fine, a little less sensitive than it could be. But technically there are other ways to deal with the fact that actually the animals are paired through the whole thing. But we're not going to deal with that today. Where did the data come from? D. Cool. Great. And secondly, I'm going to fit a second model because I am concerned about all those zeros, and that I'm only going to look at the interaction of the phase and the sex only within the shock, because in the shocks I have a lot of variance to work with. So I'm going to say model 2 is LM of time freezing, just as a function of sex and phase, where the data now come from D, but I'm going to subset it, and I'm going to say D, oops, I have to copy and paste a $sign. Condition, capital C condition, equals shock. So I'm just going to subset it to just the shocks. Don't forget that extra comma in the thing. So this only has the shock data. So it's just looking at the time-sex relationship in the shock data. Okay? Because that at least we know we have a lot more variance in the data to work with, which will be nice. So we'll do both of those. Great. So now let's go ahead and run an Anova on each one. Okay. So I'm going to actually start with model 2 because it's the simplest one. Okay. So I'm going to say, let's call it A2, whatever. This is where you can name your variables whatever you want. A2, we're going to say capital A Anova, okay, model 2. But this time we're going to pass that whatever it's called, heteroskedasticity consistent covariance matrix estimation to make sure that it accounts for some of that stuff. So I'm going to say VCOV dot, which is the parameter. I don't know why they added that extra dot. That's annoying. Equals varfun. So you can see how this code is written such that basically upon the decision of Levine's test, you can choose which one you're going to do. You could have an if-else statement, for example, right, that does that. And then you just pass varfun in here. So it could have been this. Okay, I could have just done it this way. But the reason why I chose to make that extra variable is because then you could imagine having an if-else statement up here that decides what function to use later, right? So you could do it that way. So I can run that. Okay, and you can see that it notes that coefficient covariances are computed by varfun because varfun has been changed to this function. Okay, cool. So then you can inspect what happens in A2. And there it is. So A2 detects a significant effect of phase and does not detect a significant effect of sex nor a significant interaction of sex and phase. Okay, so everybody should have this result. So make sure, I'll see if everybody gets here. Does everybody get there? Ay, ay, ay. What you do? Oh, it's a capital S. Sometimes I use capital letters for column names, and I know that messes. You can use all lowercase letters in your own code if you like, if it's easier for you. So then go ahead and run the Anova, and again, you're passing this vcov dot equals varfun, and you should get something that looks like this. So Megan, do you have that?
Mine says object time freezing not found.
That's because this first of all needs to be a capital. Oh, it's up here, my bad. And this is a matrix, so you need to have rows and columns, so you need to put this.
Okay.
Right. So remember so what does this mean? When you subset, if I just had a matrix A, this is the first row, second column.
Mm-hmm.
This is first row, all the columns.
Okay.
Right? So you're sectioning off some of the rows.
But then why is it confused about the time freezing part and not?
Because when you do this, it probably allows you to do this, but then maybe truncates a bunch of columns, and so then there's no longer a time freezing column.
Okay.
You see what I mean?
Mm-hmm.
Yeah. So to make sure that stays in there, you do that. Yeah. Yeah.
So I got it, but I have different numbers than you.
Oh, it's because you're using vcov, but not vcov HC. Remember, we decided to use vcov HC because of the departure from the Levine's test up here.
Oh, yes.
But now you can see whether or not the conclusions are changed drastically by using the correction or not. Probably not that drastically, but it looks like actually, yeah, so now run A2. So you can see it detects a more highly significant effective phase as a result of correcting for those standard errors, which is nice. Okay. So the fact that you probably have different variances when they're mostly zeros versus other things is going to impact how good it's able to detect that, right? So you do want to, in this case, definitely correct for that.
Yeah, that's a big difference.
Yeah. Well, remember, think about what the standard errors for the hypothesis tests are. Suppose you have one group that's like 0, 0, 0, 1, 0, 0. The other one's like 10, 5, 8, whatever. Because those are drastically different, the model, if you don't correct, will specify that the standard errors for everything is exactly the same. So it's going to change the denominator, right? If you change the denominator on the t-test side, but the f-test for the Anova is a similar, like if you extrapolate out. I can go over the derivation with Josh sometime if you want. But if you make the denominator smaller, suppose it predicts a standard error that is smaller than expected because of all of those groups having different standard errors, but they're predicted to all be the same. If it's smaller than it should be, or if it's bigger than it should be, let's say, then the denominator is bigger. If the denominator is bigger, then that ratio is smaller. If the ratio is smaller, then it's closer to the midline, right? So then it's going to predict a higher value for the p. So you see how that value of the standard error matters a lot.
Yeah.
Right. Okay, great. So you want to use the best estimator of that as you can, because if that number is smaller, it's going to squeeze it towards the null hypothesis. If that number can be made smaller or bigger depending on a bunch of different things. One of those things is n. It also scales with n. So as n gets bigger, the standard error gets smaller, then the ratio gets larger. There are a bunch of things that affect that. Okay?
Could you go down to your NDL2?
Yes. Let's see.
Okay, I just don't need conditioning.
Yeah, because it's only the shocks. Right. Yeah. Cool. So Josh, did you get there? You good? Okay, cool. So this detects a significant effective phase, okay, and no sex by phase interaction and no main effective sex. The main effective sex, what does that main effect mean? That means is if you average across all the phases, is there a difference between the sexes? The main effective phase means if you average across the sexes, is there a main effective phase? And the interaction means is there's some differences that are only in one sex that are different phases than another. This implies that we don't have significant effects of sex and we just have an effective phase. Okay, now you can explore what this effective phase looks like. So since we don't have a significant effect of sex, there are a couple ways to explore what this looks like. The simplest way is to make a model 3 that removes the sex. So I'm going to go ahead and do that. Because remember, since the ANOVA does not return a significant interaction or a significant effect of sex, you shouldn't really start analyzing the males and females separately. That's the rule of thumb, although people will do it because they really are like anxious to find their like effective interest. But what we can do is then just run a simpler model, so I'll call it model 3, which is just phase. So just copy that thing and remove the sex part of it, okay? And we can inspect what the coefficients look like, okay? So if I just run from the console coef MDL, okay? Ooh, model 3. Okay? You can see what's going on here. So in a simple model that doesn't have sex, you only have phase, right? This is just for the shock. So you have an intercept that's the starting expected value at phase 1, which is the tone 1, right? That's the starting expected value, so basically the average value for freezing time, right? And then these are the differences in each phase compared to this first one, okay? So what's interesting about this is that it has this like bump at tone 3, but most of these have negative values on them. So we are going down, but for whatever reason, during this tone 3 phase, there seems to be maybe a more unexpected amount of freezing. Who knows why? So we might actually then want to go in and look at the expected freezing and their particular statistics for each one, so we can make a little summary table. But let's also go ahead and run model 1 too if you haven't already. Let's kind of look at the three-way situation, and let's see if, I'm going to go ahead and put an A1 here too. Let's see if all those zeros throw it off or not. I don't know. Okay. Oh, yep. You got an infinity error. System is computationally singular. Reciprocal condition number this. What does this mean? This means that there's at least part of a matrix in there that's non-invertible. So it can't solve the system of equations. Why? Because you have a whole bunch of zeros. So it really does not like that no phase condition. What I suggest doing in this case is analyzing the no shock shock by some non-parametric method. Just like do a Mann-Whitney U test on the no shock shock and call it a day. But for these data, what that means is that the difference is so striking. You could even use a chi-square for something, for some simple stuff like that. But yeah, I don't think an ANOVA is really well posed for that because there just isn't enough variation going on in the that condition phase. Okay, so it doesn't like that, so cool. So there we go, we have our answer. So let's just finish off with model 3 now, just looking at what's going on in each phase. Okay, so I'm gonna create a new section, and I'm gonna call this section my expected values. Okay.
When you do the VCO function, why do you put the period after it?
Because for whatever reason, this function wants that parameter to be called this. I don't know why. Whenever probably because to distinguish it from the function that's used at large, like system-wide. I don't know. But if you read the manual on this particular function, that's how you specify that thing. It's this. It's this equals something. And then you put it in there. So I don't know. That's just what they decided to call it. Periods don't do anything in R, so you can have a period as part of, I can say, it's not like MATLAB. I can say a dot equals 1, and then a dot is my variable. Because you can make a variable name anything. So periods are meaningless in R, so they can be part of a variable name. So people will use them sometimes in these dummy parameters to functions. So remember the equivalent of, in MATLAB, this is doing the same thing the $sign does in R. Okay, but the period in MATLAB doesn't do anything. The period in R doesn't do anything, so you can have it be that. Okay, so let's go ahead and do some expected values. We'll end there, and then maybe I'll whip up what some of the actual pairwise hypothesis tests might look like. We can see if we can finish that up here in the last couple minutes. Does anyone have anything pressing in lab they want to get to that we want to wrap up like right now, or are you cool to chill for like 5-10? All right, sweet, let's do it. So expected value table, this is just my summary table of all the means and their standard errors for like my graph or whatever, or just for reporting. Okay, so I always call this X data, which means example data or expected data. That's just what I call it. So for this, I'm going to go ahead and do, now, if I were doing the sex and the phase, I'm going to do that from model 2 just to show you how to do it, but then I'm only going to do the pairwise tests for the phases because we know there's no significant effect of sex, allegedly. So I'm going to go ahead and do this. So I'm going to use the expand grid function, expand.grid. I'm going to say sex equals levels d, oh no. Yeah, it's time for a new computer. I'm going to talk to Shrek about that because he'll probably buy it for me. Ah. Levels d sex. And then phase equals levels d phase. So what does this do? Again, so if you run this, this is going to create a table that looks like this. Female tone 1, male tone 1, female tone 2, male tone 2, and so on and so forth. It's a very quick and easy way to make a table for summary of like all the possible things. Okay? Because this is the summary table, and then the next column, unsurprisingly, is going to be the averages and the standard errors and like all. I'm trying to make a summary table to export or to use for my graphs or to report for my paper or whatever, right? Okay, great. So now I'm going to make what does the actual matrix look like that models this. So I always call that x. X equals model.matrix, and then I'm going to copy the formula from above here, which is sex times phase. Okay. So there's no y, that we're just looking at whatever the function of sex times phase is, where the data come from this matrix, or this table rather. So x is the actual modeling matrix. That looks like this. It has all the columns for all the betas and all the ones and zeros. That's this ugly thing. Okay. So there's a tilde, sex, asterisk, phase, data equals x data, cool. So now we can actually put in all the values. So x data, no. Mean estimate. What is that? That's x. Not my percent sign also not working. Oh, guys. This is the worst. Thank you. And this is model 2, right? Yeah. So x asterisk, percent sign asterisk, this is matrix multiplication. What is this going to do? It's going to output all of the means. Okay? Quick and dirty. Boop. So now, that has been added in as this new column, which is called mean estimate. So this is the mean estimate of freezing time spent freezing for each of these things. Okay, cool. Now we need the standard errors for this. X data, $, standard error, let's call it. How to calculate this? Remember, it is the square root of the diag of the matrix, which is the V-cove matrix. Okay, we got to wrap it in this x stuff, so this is ugly. I'm so sorry. Oops. Did I do this right? Yeah, I did. Great. So it is x times V-cove, in this case V-cove HC, model 2, times x transpose. Okay? This is the matrix of, this is the vector of standard errors. Boop. And there you go. Okay. Ugh. Oh my god, I don't want that. Great. So then we can do some more things. Well, let me make sure everybody gets here. Remember what you're getting is, just very quickly. Does everybody get there? Okay, everybody got there? Okay, I'm not going to explain the math part then. That's matrix math. So that's linear algebra. That is taking a row, multiplying by a column, and adding all the numbers together, and then repeating. So that's, because the asterisk by itself is just element-wise multiplication. So this, in MATLAB, the asterisk is used for both things, so that can get tricky. But in R, percent sign, asterisk, percent sign is matrix math. So yeah, that is basically, because what you're doing, I'll go ahead and do this because it's worth belaboring, I suppose. What you are doing is you are computing x times v times x transpose. Okay? I made that ugly because I couldn't see my cursor for a second. So v, remember, matrix V contains the standard errors for each of the beta values in a regression model. So if you were just doing the test that any one of these b values was equal to 0, then your standard error term could be derived from this diagonal. And the mistake that I wrote here is this should say sigma b0, sigma b1 for the covariance terms. So in general, we think of variance as additive. If I have some relationship where c equals b plus a, I can think of the error in, or the uncertainty in c as equal to the uncertainty in b plus the uncertainty in a. And if we suspect there is covariance plus this term. And in general, how do we extrapolate this to matrix math? Well, let's consider we have a vector that describes this particular operation. So let's say we want the quantity b star, which equals b0 plus b1. Well, if I have my vector, and that vector is b0, b1, b2, and my operation is b star, and this row vector has the coefficients 1, 1, 0. Let's call this vector LC for linear combination. Let's call this vector LC for linear combination. We know that if I take LC times B, I'll get B star. Why? Because if I take this and I multiply it by B0, B1, B2, I get exactly the quantity B0 plus B1 by matrix math. So now, if you then want to consider what's going on with the errors in this, let's consider the same combination. So B star, B0, B1, B2 is 1, 1, 0. Let's see what happens if we multiply this times V. Then times B star transpose, which is 1, 1, 0. Let's actually do the math out to prove it to ourselves. Oh, come on. I keep hitting this thing. Okay, so again, and when you do this matrix math in R, I really recommend that you label your rows and columns of your matrices. It really makes it easier for you to make sense of what the answer looks like and whether it's the answer that you want. Let's fill this in and do this all by hand because we got time. Sigma squared of B0, sigma squared of B1, sigma squared of B2, and let's split the off-diagonal terms. Sigma of B0, sigma of B1, sigma of B1, sigma of B2, and sigma of B0, sigma of B1, and of course it's the same on the lower triangles. So this is a 1 by 3. This is a 3 by 3, and this is a 3 by 1, and as we know, the inner dimensions cancel, and we end up with a scalar 1 by 1. Okay? Cool. So that works. So let's start with the, let's make this smaller. Start with that left-hand side. So just considering this part, because remember in matrix math we move from left to right. So we got 1 times sigma squared B0, right? So that is, so this is a 1 by 3 times a 3 by 3, which means the answer has to also then be a 1 by 3. So we're going to do this part first. We're going to get a 1 by 3. So let's do it. 1 is sigma squared B0, so we got that. Cool. And then plus 1 times sigma b0, sigma b1. Okay, so we already see this is working, right? And then 0 times the last term. Okay, what's the next element of this? Well, let's multiply by the next column. 1 times sigma b0, sigma b1. You can already see where this is going, huh? 1 times sigma squared b1. And then 0 times sigma squared b2. Or sigma 0, sigma b2. And of course, I didn't make this far apart enough. And what is the third element? Okay. That's 1 sigma b0, sigma b1. 1 sigma b1, sigma b2. Now you're going to say, Mike, that doesn't end up in the answer, but you'll find out what happens. 0 and sigma squared b2. Okay, we got that 0. Okay, now we're going to take this, but now you can already see, because this last term here is going to be multiplied by 0, which is why it doesn't end up happening. Oh, it does end up being part of the answer. So now, let's multiply it by the transpose, 1, 1, 0. And what do you end up with? Aha, you end up with sigma squared b0 plus sigma b0, sigma b1. Okay. And then 1 times the next term is sigma b0, sigma b1. So it's 2 of those. And then sigma squared b1. Ta-da! And then 0 times the last term. And so your answer is exactly what we said before. Sigma squared plus 2 times the covariance term plus sigma squared b1. So that means the standard error, well, I'll just call it sigma, I guess. Sigma of b star is equal to the square root of sigma squared b0 plus 2 sigma b0, sigma b1 plus sigma squared b1. Okay? So in general, if you have any matrix that has combinations, addition, subtraction, linear combinations, call that X. Let's call it W usually for weights or just some sort of combination. If you want to find the variance-covariance matrix that includes the new standard errors of those combinations, i.e. all of these wacky things, it's just going to be W times V times W transpose. Okay? So anytime, whether those, so W could be combinations that are the group means, right? So the means are combinations, right? So if we remember from a typical model, mean A is just maybe B0 and mean B equals B0 plus B1. So this vector is 1, 0, 0. This vector is 1, 1, 0, right? And mean C is B0 plus B2, right? So maybe that's 1, 0, 1. This is W, okay? So if you want the standard errors for each of these means, that's W, V, W transpose, just as we described. And that's going to have all those off-diagonal terms and account for everything in this final equation. But W could also be linear hypothesis tests, right? Because remember, mean B minus mean A, that's a hypothesis test. That's equal to the value of B1. So that, what's that vector? 0, 1, 0. And then, if we remember correctly, mean C minus mean A, that's the value of B2 maybe, which is 0, 0, 1. And mean C minus mean B, well, that's going to be these two subtracted minus each other. So that's going to be B2 minus B1, which is 0, minus 1, 1. And then this becomes W, right? So no matter what W is, so if you want the standard error associated with this test, or this test, or this test, it's always as W times V times W transpose. Then, whenever you take W times V times W transpose, you end up with a matrix that's square, right? And that matrix is going to have, you know, combination 1, combination 2, combination 3. And it's going to have the sigma squared for the combination, the sigma squared for the combination 2, sigma squared for the combination 3. It'll have some off-diagonal terms, potentially, although hopefully your data don't have too much autocorrelation. And where each of these combinations are things that look like this. But because we are doing it in matrix math, it's a lot easier to compute than having to actually calculate all these things. You just do W times V times W transpose, or in R speak, that's W percent sign times percent sign, V percent sign times percent sign, I can't write a percent sign, times TW, right? And then you just take the square root, oh boy, that was ugly, the square root down this diagonal, right? The square root of the diagonal of W times V times W transpose. Boop. And that's it. And now finally, just to sort of relate it back to what we're going to talk about later, your choice of V here, okay, could be the one that is the homoscedastic one. That's the one that comes from linear regression model, but that's the homoscedastic one. That assumes that V is this thing, which you can look up, and we're not going to discuss it more today. That's this, but actually V can be anything, and there could be corrections that you make for this that allow different groups to have different estimates of sigma squared. This is the simple mean standard error of the residuals that comes from linear regression, and the assumption is that this is going to be good enough for all the groups and all the variation in the data. But in real life, we know that data can violate this, and so there are various homoscedastic consistent versions of this, various corrections to that, and that's what we're going to discuss using the vcov HC function, which comes from the sandwich package. This is an abbreviated form of what the original expansion is, and the original expansion looks like this. It's X transpose X inverse X transpose sigma squared identity X times X transpose X inverse. This thing basically becomes this. Okay? Why is that so? This is the actual derivation for V from ordinary least squares. Why does this work? Well, this is the inverse of this. If sigma squared is just a scalar, that comes out. This thing is just the other, that's the non-inverted form of this thing, so that just is the identity, and then multiplied by this is just this, and so you end up with this. But if you look at this, this is a matrix that has sigma squared, just that single value, all the way down the diagonal. Alright? So, V in general is X transpose X minus 1, or inverse, X transpose this matrix with sigma squareds down the diagonal. And this is where the various estimators that are robust against violations of homoscedasticity come in, because you could imagine replacing these values or scaling them somehow with different metrics or different ways of scaling these to have more robust standard errors for the final V matrix. And so there are lots of different options for this. This in general, this term in the middle here, which is called the meat. Econometrics people call this the sandwich. They call these parts the bread. And they call this part the meat. Which, I mean, not very vegetarian friendly if you ask me. And that's why the package that was built for R is called the sandwich package, because it's based upon this principle. So you could take this matrix that's in the middle here and just replace it with something else. And people have made various decisions. There's the Huber estimator, the White estimator, the Halbert White is his name, I guess. There are a bunch of different people, a bunch of different old people from various parts of the 20th century that had different opinions on how you should alter this matrix to make it more robust against violations of the assumption of homoscedasticity. And those are all included in the sandwich package. And there's a paper that's listed. If you look up the vcov HC function, if you look up the documentation for that function, it lists a bunch of references. And you can go through the references. A couple of them have different choices for this matrix in the middle, the meat matrix, and how those researchers dealt with the problem. And there's one that whoever wrote this package decided was the best. There's one paper that seems to decide that one of these versions of this is the best performer by running some computer simulations with data. So you can use the default. In practice, I find a lot of them don't differ that much. Anyway, this is just to correct some mistakes I made on the board, but now back to the regular scheduled programming. We can also then calculate the 95% confidence intervals on these estimates. Those are typically the things that I like to plot on the graph. You can also plot plus or minus standard error if you like. Now, mind you, when things get low to 0, you might get into trouble. Some of these values might dip into negative territory, so keep that in mind. If you are doing Anova-like statistics and they can dip into negative territory, you might consider just putting the mean lines on the graph, because everyone always raises their hands up in a tiff of like, that standard error is going below 0. That's impossible. What does that mean? So keep that in mind. I'm going to say that the let's call it the LWR for the lower 95% estimate. Okay, what does that equal to? This plus this. It's a multiple of the standard error, right? That's what that is. If these were normally distributed, it would be however many, isn't it like 2.5 standard errors? That's like almost the 95, like something like that, right? But we don't, in linear modeling, we don't use the normal distribution for this. We use the t distribution for this. So it's a multiple of, it's a t multiple of the standard error. So I'm just going to multiply this times the t quantiles, that's qt, okay, for 0.025. Oh no, my 5. Oh God. Because remember, the 95% confidence is from the 2.5% quantile to the 97.5% quantile. Oh my God. This is awful. I gotta get this fixed, you guys. I gotta get a new computer soon. Where the degrees of freedom for this come from. The degrees of freedom in your model are stored as model 2. df.residual. Oops, let me scooch this over. You can just tab to complete it. And I'm going to copy and paste that line and call upper 9.75. Okay. Great. So from the 2.5% to the 97.5% ends of the t distribution, that is centered around this estimate with this standard error, basically, right? That's what that means. So if you run both of those, now you have, oops. Now you have these lower and upper confidence bounds for all those things, okay? So some of them might be a little wide, but these are 95% confidence intervals, right? And you can see why there's not a detected sex difference. So let's look at the confidence bounds for each of these things. The males stretches from 1.8 seconds to 6.8 seconds. The female stretches from 0.12 seconds to 5.4 seconds. So you can see that this confidence interval on this mean is completely inside this one. So there's no significant difference there between those two. And that's similarly true for all of these. You got 0.25 to 2.7, 0.48 to 1.5, so on and so forth. And then you got 0.48 to 1.5 and 0.073 to 6.5 and so on and so forth. Okay, cool. One thing to notice is that, oh yeah, this is tone 2, right. Interestingly, that weird effect in the phase betas, where beta 3, or not that one, where was it? Up here somewhere. Well, there's a weird effect where it seems to like bump strangely. That seems to be coming somewhere from here, probably because these confidence bounds are really well. Actually, both of them are. This, like for some reason, at tone number 3, we're back up at like 3 seconds and 5 seconds. Now, it doesn't appear that this would be statistically significant difference from like tone 1. For some reason, we take a dip at tone 2, and then we're back up at tone 3. And I don't know why that is. and then we stay up at tone 4, and we stay up at tone 5. So we have a dip, and then we come back. Did someone accidentally turn the foot shocker on? Because that would explain that, right? It's like they were forgetting the memory, but then somebody turned the foot shock back on, and that's why they came back up. I don't know. So okay, so then this has your expected values for everything. Okay, great. So the last thing that I want to do is we had a significant effective phase, right? So let's do pairwise comparisons between the phases. Okay, this is the last thing that we'll do, just the last couple minutes. Hopefully people have time for this. But this will give you kind of everything you need. Now remember, we're going to use model 3 for this because we decided there's no significant effective sex. We're just interested in the pairwise comparisons of the phase. Okay, cool. So I'm going to use, from the multicom package, I'm going to use this contrast matrix function. Okay, so I'm going to call this, what do I want to call this? Comparisons. Let's call it comparisons. Equals COTR, capital MAT, the contra-mat function. I'm going to give that this is an annoying function to use, but basically you have to pass to it a particular kind of data structure called a table. I'm going to call this table x data $ phase. It's just like, it just needs a vector list of all the phases. So, but it wants it to have like a number attached to it. It kind of doesn't matter what it is. But as long as it's a vector that looks like this, in this case, that particular matrix has like 2 examples of each of those. It doesn't really matter how many there are. You'll see what the output looks like. But the type, for all possible pairwise comparisons, which between the phases kind of makes sense, I'm going to use a capital T for Tukey contrasts. That's what that means. The Tukey method is looking at all possible pairwise comparisons of things. When I do this, I end up with this matrix. So that's this thing that we made in Excel by hand the last time. So you can see we have a tone 2 minus a tone 1, and a tone 3 minus a tone 1, and a tone 4 minus a tone 1, and a tone 5, and then the individual comparisons between each one. So there's a -1 and a 1 in all the columns where you're taking one thing and subtracting the other thing. Do we all see this? This is the thing you should end up with. So this is the call, and then these are all the thingies. Let's see. Forgot the parentheses. There you go.
Why doesn't it just tell me that?
Because
Like that error is horrible.
okay, there you go. Okay, so now inspect pairwise. Just like look at it from the yeah, there you go. So that you should have this kind of a thing. So those are all the things. Now again, I'm using the quick function to do this. But if I had a planned set that was more limited, I could just like make that myself, which is what we did in Excel maybe I think the last time. So it depends on your application. In this case, all possible pairwise comparisons kind of make sense because we're looking at all the differences between the phases. So it makes sense to do that this way. So I'm just using the quick function that does that. If you have something planned, you obviously can make this in Excel. Okay, and then I'm going to make my actual testing matrix. So I always call that lowercase cx, which is comparisons. %**% x. Oops. So basically, I'm multiplying these comparisons to x. That's going to do all the possible different row combinations on x, basically. Whoops. Why do you say that? Why? Oh, my bad. Oh, damn it. It's because x has the male and the female stuff in there, so I'm going to make a new x, x2. Matrix, give me just copy some of these lines and get rid of the sex part of it. x2. I'm just going to do this quickly like this. You can do it in a couple lines if you want. I basically just want a matrix that is, oh, there we go. There we go. I'm going to put this line in the Slack so you guys can copy and paste it. Oh, ad block, I know. I know, just like you're just aggressively opening a new tab. I didn't want all of that. Okay, Oh my God. Why are you doing this to me? Okay, there we go. There we go. Ultimately, you need something that looks, whoops. Yeah, something that looks like this. And so I'll just put these 2 lines in the Slack for the stats workshops. There you go. You can copy those out of there if you want. Now, once I have this comparisons matrix, I can pass this to the multcomp function. So I'm going to say my hypothesis tests is GLHT. Again, that's the general linear hypothesis test function from the multcomp package, where the model comes from model 3, and we're passing CX to it as this linear factor, whatever matrix that it wants. But then we're also going to pass the standard error function again, where vcov equals vcov HC of model 3. You use that var fun as well that I used before, because I specified it above. But regardless, you could do that. So once you have all this stuff, you can do this, and that runs that thing. So if you have that working, now you have all of those. These are the estimates for all those tests. Okay. So for example, the tone 1 minus tone 2 is reduced by 2.3 seconds. And then to actually get all of the significant statistics from that, you just run the summary. So I can run a summary of hypothesis tests. I could save that to something and export it if I want. And when you do that, you get something that looks like this. Okay?
We get VCOV method for model. No VCOV method for model.
Okay, is this, first of all, is CX correct? Okay, cool. No VCOV method for model found. Okay.
Does it need the period?
It has it. No, that's a different function. This function shouldn't care about that. Oh, this. There's just it gave you a weird error, but it was just a mistake of the spelling of that particular parameter. Oops. There you go. Okay. And then if you run the summary on that, you'll get this thingy. So after correction for pairwise testing, the only one that seems to make it through is the tone 3 versus tone 2. There's at least a trend in the reduction of tone 2 versus tone 1. But the data are not as robust. And consider the fact that for most of these, with the exception of that tone 2 section, most of these guys, there isn't that much reduction by the time you get to tone 3, tone 4, and tone 5. Now, there might be a difference in just the last 2 seconds. Right? You might consider, you can now use this as a template, right? You can actually rerun all of this for just that last 2-second thing, for the first 10-second thing. You can mess around, you can kind of see how you would do that. But the data are not as robust as they might be. Now you can see what happens, by the way. I'm curious, I'm just going to run this as the last thing. You can kind of see what happens. I'm going to call this, if I didn't use the standard error correction at all, and I just allowed it to estimate the standard errors to be the same. One thing you notice is now you have the problem that the denominators are all identical. That's what homoscedasticity means, is that all the comparisons between groups have the same standard error. Now you've really taken a shit to even detecting that initial trend, right? By not correcting for those standard errors that are different between the groups. But yeah, so this is the issue with this. So this is highlighting why you want to use corrections to that, because in cases where you do have these extreme departures from that particular thing, if you just let the Anova and the linear test do their thing, it's going to say the denominator for all of these things is identical, which is probably not reasonable. Whereas if you do this, by the way, it doesn't affect the estimate. It just affects the standard error, and then it affects the t-value, which is this divided by that, right? So the estimate is the same. It's negative 2.3 seconds. It's about the uncertainty in that estimate. In one case, it's going up a little bit more than it is if you estimate a group-specific standard error. Okay? So that's that. And that's the basis of how you do all of that. Now for that no shock versus shock condition stuff, I would recommend maybe using some non-parametric or some not Anova thing, because all those zeros, that's going to really mess everything up. That's really going to be hard to split those up. But there are two different questions going on. I mean, that kind of tells you what you need to know already, is that in the no shock condition, essentially nobody froze. So you don't really need a significance test to tell you anything like that. You could just kind of say, well, nobody froze. So so there's not really much to say. You could just report that. Like, I would say that's pretty significant. Like, you don't need a test to give me an answer to that. You know what I mean? So it's mostly within that shock, like what the slopes or things are doing. This is kind of telling you that across the 5 tones there isn't much extinction, which maybe you already noticed. I don't know. But anyway.
I think it would take a couple days.
Oh, really? Okay, so maybe.
People have found sex differences in extinction where they do one tone without the shock, and then they repeat it like a week later.
Oh, so maybe that's what you should do for that. But yeah, at least in this is all within one session. Yeah. So.
Needed the brain sound.
So this tells you that there isn't much difference within one session, which maybe confirms something you might have believed already. I don't know. Cool. Great. Well, that's all.
Okay, thank you.
Yeah. So I'm going to send put the complete code in the chat. And then you can use this, like I said, as a template for like other things that you have to do. So hopefully this is helpful in that way. And then in the pinned post on this chat is my Dropbox folder that has access to all the folders, so you can just kind of get that. This is the complete analysis code. Cool. Great. Yeah, okay, thanks.